Okay, we're going to continue. Now, whenever you come across a graph, I want you to, before you answer a question, I want you to try to understand the graph. So one I skipped here was this one here. And that's because it would require using the quotient function, and it can get quite messy. So it's for C. We already did A. And fortunately, they just want to know the value of the second derivative and a rough idea of what's going on. So that means we have to take the first and second derivative of this, but I want you to understand this graph. What happens down here? When I square any number, whether it's negative or positive, it's going to become positive. Then I'm going to add 1, so it's always going to be above 0. So I'm never going to have a square root of 0 down here. And that means this number will essentially become, what's the square root of w squared? W plus the square root of 1, essentially. So slightly above w. What's going on above this line? Well, that can be negative or positive. So on the left side of the y-axis, I get negative w's, and on the right side, I get positive w's. However, it's always being divided by a positive number. So that means this side of the graph will always be above the y-axis, and this side of the graph will always be below the x-axis, above the y-axis and below the x-axis. What else is going on? Well, if the bottom is essentially this w, and I'm taking the top and dividing it by w, as I get to negative infinity, I will have negative 1. And as I get to positive infinity, I will get to positive 1, which means there's going to, and by the way, because the bottom is always adding a tiny number compared to it, it's always going to be slightly, but never reaching 1, which means we're going to have horizontal asymptotes. I'll try to get down to it here, which means you're going to have horizontal asymptotes at y is equal to minus 1 on the left side, and y is equal to 1 on the right side, and it's never going to reach it, which means you're going to have a graph that does something weird. Something like that. And I'll just make it in green. And I'll try that again. And it's going to do something like this. And I don't quite have it right. Maybe like that would be more accurate. And like this. There we go. So you're going to have something like that. And that makes sense, especially if you take a few values here, like what happens when w is 1. You get 1 over square root of 2. So square root of 2 is like 1.4. So 1 divided by 2 square root is equal to 0.7. It's going to be about here. Same with minus 1. It's going to be about there. Does that make sense? What about if you take a big number like 10? So 10 divided by the square root of 11, essentially. Or square root of 101, rather. 101. So you take 10 and divide it by the square root of 101. And you can see you get almost 10. You get 0.999. So that means that's already when we hit about 10, it's trying to reach 1. Same with on the negative side. Go ahead and throw in a couple numbers to figure that out. So when it's probably around 3 and 0, it has this weird transition phase, and that's because the bottom number and the top number will come out to below 1. Below 1. Go ahead and try it with 0.5 and you'll see. And you can always punch it in Desmos. But that means the derivative, the slope here, is going to be positive. And then same with here and here. I don't think you're ever going to have a negative slope on this, which means the first derivative will be positive. There might be an inflection point there, but I don't think so. So overall, I think the second derivative, because we're always looking at, oh, actually, no, this is going to be down. So on the right side, the second derivative is going to be negative, and on the left side, the second derivative is going to be positive, because it's a concave up, concave down, which means there's probably an inflection point at 0. But let's go ahead and take the first derivative. So the first derivative quotient says I'm going to take the bottom, let's call the bottom function, I'm going to multiply it by the derivative of the numerator function. I'm going to subtract the numerator function times the derivative of the bottom function, the denominator function, all divided by g of x squared. I'm going to square the denominator. So let's look at what we have. The numerator function is w, right? Its derivative, so f of x is w. Its derivative is 1. The bottom function, g of x, is the square root of w squared plus 1. And to take the derivative of that, you have to turn that into what it actually is. It's w squared plus 1 to the half. That's what a square root is. And to take the derivative of that, you have to do the chain rule. W squared plus 1, and you have to lower the derivative by 1. So it's going to become minus a half. And then you have to multiply that by the derivative of what's inside, which is 2w. So that means as a numerator, I'm going to get 2w. And at the denominator, I'm also going to get this 2 times something. So that means the 2's will cancel out. So I'm going to get w at the top. I'm going to get at the bottom now this. So this is the first derivative. That's what w squared plus 1, this should be a square here, to the negative half means. It means it goes down to the denominator, and the half means square root. The 2w here stays on the numerator, but this 2 over here is on the denominator, and that's why we're left with a w. So this is the derivative of the denominator function. And you can see how complicated it gets, right? So that means if I replace on the left, I have to replace it with this times 1, so it's just 1, minus this times this. Okay, and what's this going to be? W times w, it's going to be w squared. So I'm left with this. What's on the bottom? It's going to be this squared, right? Which will essentially just be that. But let's just leave it like that first. Keep in mind that this, in order to subtract it, I have to make it, because it's being subtracted here, I have to put it on the same denominator, which means I have to multiply it by this whole thing over 1. So I have to multiply it by this whole thing over 1 in order to get them as the same denominator. It's clear that when I multiply them, I just get w squared plus 1 at top. And then I have to subtract the w squared. So I just get 1. And since I've made the denominator the same, it is simply, the top simply becomes this. This is what happens when I subtract them. If you can't see it, let me know in the comments and I'll redo it. Now suddenly I have this divided by what is essentially this fraction down below. And to multiply fractions, you have to take the reciprocal of this and multiply this fraction. So I'm really going to take this 1 and multiply it by, get rid of this fraction. Let's try doing it like this. There we go. There we go. And when I have they have the same denominator. This one is to the 1, if you want. This one is to the 2, so it becomes this to the 3. If you want to express that as a brackets, you can do this. It becomes, or you can just do this actually. It becomes w squared plus 1 to the negative 3/2. And the 2 represents the square root, and the negative number means, and the 3 represents the cube, and the negative means it's in the bottom. So this is essentially the same expression. And so all of a sudden, we have the derivative in 2 different formats of the first derivative of PW. So we're going to make this equal to the first derivative. They're both the same, by the way. Let's see if I got that right before I continue so that I don't make a colossal error. So this is question number, what are we on? Over here, right? Oh, so it's got to, it just gives the answer. Okay. First of all, let's see where the point 3 lies on this graph. The point 3 lies on this graph. I'm given 3 over the square root of 10. Right? 3 squared plus 1. 3 divided by the square root of 10 is 3.11. Oh, that's not right. 3 divided by the square root of 10, I forgot to hit equals, is equal 0.94444. So that means that 3.948. It's 3 comma 0.948, whatever it was. So it's almost reaching the, if this is the graph, it's coming up and it's almost reaching 1 right over here. So it's clear that it's sort of going to be on the top slope, so I'm expecting a positive slope. It's clear it's concave down, so I'm expecting a negative from the double. Let's see if we get a positive at 3 into the first derivative. So you get 1 over the square root, or if you want, 1 over 310. And after to take the square root, I'm putting it to the power of 3. So it's clear it's going to be a small positive number. 1 divided by, and let's just take 10, and we're going to take the square root, and then we're going to put it to the power of 3, and then we're going to just take the reciprocal so that we get the 1 divided by 0.3001 positive. So we can see 0.031 is the first derivative, so it's a very gentle slope, but it's positive. Now let's take the second derivative. Let's try this again. The second derivative, we're going to use this so that we only have to use the chain rule. So this goes down in front. I get minus 3 over 2. I have to lower minus 3 over 2 by 1, so it becomes minus 5 over 2. This stays in the bracket as is. And I'm multiplying it all by the derivative of that, which is 2w. Right away I can see my 2's cancel. I'm left with minus 3w at top. So I got minus 3w at top. And at the bottom, that 5 over 2 simply means I'm bringing the whole thing down to the bottom. I'm taking the square root of it, so it's essentially this. Only this time, I'm putting it to the power of 5. That's what negative 5 over 2 means. And it's like this. Now notice the only thing that's changed in the numerator is it went from positive to negative, which means our result this time will likely be negative because the bottom stays positive with that square root going on. So for 3, we can see the top becomes minus 9, and the bottom becomes 3 squared plus 1 square root of 10 to the power of 5. Square root of 10, which is 3.3 something, to the power of 5. So you're going to get something like 3 times 3 times 3 times 3, 81 times 3, you're going to get like 260. So minus 9 divided by 260 becomes a negative tiny number again, which means, as predicted, this dot is part of a concave down loop because of the negative double derivative, but it's below the peak of the concave because the slope first derivative was positive, which matches what we think the graph looks like. So let's go to this. Here's the graph. I've done it for you. I'm going to take f of x. There it is as expected. I'm going to put down the spot 3 comma f of 3. I'm going to show you the derivative at 3 is indeed what we got. And I'm going to show you the second derivative that 3 is indeed a negative number. I'm also going to show you that number 1 over the square root of 10 to the power of 5. And it's indeed, when it was 3 times 3, so it's 9. And it's indeed the same number that we got here, except I have to remember to do negative 9 here. And you can see that we got the calculations right. Okay? Instead of doing it on the calculator, I'm just going to show that Desmos match, these numbers match, because this is Desmos calculating the derivative, and this is what we came up as the derivative. All right. And we can see as we zoom in, it matches what we expect. It's on the way up. So this whole thing is a concave down. So if I were to put it in like a parabola thing, I would get x minus 3 squared negative plus 1 or plus 0.9487. So you can see that that dot is sort of on the way up of that parabola, which is the concave down. And I'm just putting it there to illustrate why the double derivative was negative. And the graph is exactly as predicted. Moving on. I'm sorry if I kind of ramble, but it helps to understand what they're measuring. So number 5 has a few parts here. And they ask a few questions. But first, before we get to that, they're giving us the second derivative of a function. And second derivatives came from the derivative of the first derivative. And I already know the derivative, if it comes out of line, the derivative before that, the first derivative, was a parabola. Because if I take the derivative of x squared, I get 2x, which is a line. Which means the original function was an x to the cube. This is important for you to understand, especially as we get into integrals. So that means the original function of this second derivative graph was a cubic. And it has a negative slope as a second draft on overall. Well, actually, no, it's only negative over here. And it's positive here. So that means we're dealing with probably a cubic that goes like that. Okay, where this would be, oh, actually, no, it would be like that. Where this here would have a positive double derivative, and this would have a negative double derivative, and this would be the inflection point. So let's go back and learn what this means. So if you look at the part I'm highlighting in red, it's clear that the double derivative here is positive, right? What does a positive double derivative mean? It means that entire part is part of a concave up. And what does it mean when the double derivative is 0? That means that's the inflection point where it starts to turn and become concave down. What does this negative mean? It means from that point on, from that inflection point on, it's concave down. Which tells me that this cubic is going to have a negative leading because it's starting up here and instead of the usual down here. It's going to start by going down, and then its inflection point is going to become up. Now, they say, on which intervals of the graph is it concave up? So it's everything to the left. Oh, concave up? No, concave. Oh, concave up. So this is concave up. So everything to the left of the inflection point. So when x is smaller than 1. And on which interval is it concave down? So that's this point. So it's every spot above 1. Then they say, what's the x-coordinate on the point of inflection? It's right when it hits the x-axis. So that's when y is 0. So it's right there when x is equal to 1. So we can see everything to the left of the inflection point, because it's positive, is going to be concave up. And we can see everything to the right of the inflection point is negative here. So it's going to be concave down after the inflection point. So you're going to be looking at a graph very much like I've drawn, like this. Now it goes on to say, make a rough sketch if f of 0 is 2, which means after the inflection point, this here is going to be 0, 2. So when x is 0, it's going through the y-axis at 2. So it's roughly going to look like that. It's going to come down, go through the y-axis here, and because the inflection point is at 1, which we've determined here, it's only going to start turning around and becoming concave down at this point onwards, which I'll draw in green. So that's roughly it. Let's see how we did. So it's saying it's concave up when x is less than 1, which is what we've said here. And it's concave down when x is bigger than 1, which is what we said here. And the inflection point, we said when x is 1, which is what we said here. And they've done a rough graph, except they've done a little slip slide thing here. So they've made the inflection point here. So instead of doing a big loop like we did, they did a thing like that, which I guess can make sense. So this is also possible. Yeah, there you go. So they've just made it a little flat, but they still made this part here concave up, and they've still made this part here concave down. So there you go. And that's precisely what we wrote down here when we said this, and x is equal to 1 here. Okay, let's look at the other one. The other one, let's ask ourselves what this is. It's a parabola, right? So that means if the parabola is the second difference, a cubic is the first difference, and a quartic is the next difference. And we know that quartics will either look like that or they'll look like that. Okay? Now let's look at the inflection points. The inflection points happen to be where 0, so that means the curve's going to change. What happens on the left here? The double derivative is positive. So on the left, we're dealing with a concave up situation. So we're dealing with that. Then right here, when it hits the x-axis, I'll do the x-axis, or the y-axis, sorry. It's going to start the inflection point, and from that point on, the object is going to turn. Okay? And by the way, this inflection point doesn't have to be on the x-axis. I just mean that that's when 0 occurs. And actually, I should skip the axis and just draw it like this. So at this point here, which is x of 0, when x is 0, we have an inflection point where it starts going the other way, concave down, because we have a negative. Everything is negative from 0 to 2 there. Which means over here, at x is equal to 2, we have another inflection point where it has to come up again. Since w's, or cubics rather, can only have 2 inflection points, well, actually they can have 3, this is either half of the image or only part of it. Actually right here, that's technically 2 inflection points, so it would look like this if they've shown us, yeah, and they've shown us all of it. And then on that point onwards, after 2, all my double derivative is positive, which means I'm dealing with a concave up, so that explains this. So if I had to draw it, since there's only 2 inflection points, I'm going to do a slip and slide here, or I might do a slip and slide there, like that. Now they're saying When is it concave up? Okay, it's concave up when x is smaller than 0, and it's concave up when x is bigger than 2. When is it concave down? That's when the double derivative is negative, so between 0 and 2. So when 0 is smaller than x is smaller than 2, it is concave down. And then finally he says, where do the inflection point occur? Well, when x is 0 and when x is 2. And what might the graph look like? Well, it would look like this. And this part here would go through the y-axis. So this part here would be up above because they tell us f of 0 is 2. Let's see how we did. Okay, they're telling us that it is concave up below 0, which is what we've discovered here, and above 2, which is what we said here. And they're saying it's concave down between 0 and 2, which is what we said. And we said the inflection points were 0 and 2, which is what we said. And look at that. Our drawing, they have it going down here, but it's got to come up if it's an x to the 4. So they only gave us partial. But it actually makes sense because that's turning the whole way. So it's going to come back up. But they did only give us this, and we got the drawing almost exactly. Almost exactly. Okay. Those are probably, more conceptual. Number 6, you should know very well because you're going to have to graph. Whoops. Number 6. There we go. It's a very straightforward question, but you should know it. Okay. How to use the second derivative to determine a local maximum or minimum. So first, you've determined the max or min using first derivative equaling 0. And you found out the x values when that happens. You then take the second derivative and plug in those x values you found in the first derivative. If the result is negative, you have concave down, and if the result is positive, you have a max point, a local maximum point. If the result is positive, you have concave up, meaning it's a local min point. There you go. That's exactly how you should do it. You have to figure out from the first derivative first where these x values are when the result is 0, because the slope is 0 at local mins and local maxes. And once you find those x values, you must plug it into the second derivative formula and figure out the result. And by the way, if the result of the second derivative is 0, you need to investigate further, because you're probably dealing with an inflection point, not a local min or max. There you go. You can see it's sort of important to know that. I'll let you do this because it's pretty much what I described in 6. It's just going to replace, instead of taking, once we find a max and min, we used to take the slope to right or left. And instead of doing that to see if it's a max, because if the slope was positive and negative, positive to the left and right, negative to the right, it was a max. If it was negative to the left and positive to the right, it was a min. So instead of doing that, we're going to take the second derivative, if it's easier, and plug in the x values as I described in number 6. Okay, that's it, really. For each of the following, determine any points of inflection. So we need to know the second derivative. and use the results in part I, along with the revised algorithm, to sketch each function. Okay, well, before we continue, let's look at each function. This one should be easier to sketch. Let's take an x out. We've got x cubed plus 4, right? When will that be equal to 0? Well, when x is 0. What is it, by the way? It's cubic. All right? So right away, we can say that there's going to be an x-intercept here, 0, 0. So there's no y-intercept. It's going to go through 0, 0. What else can we say? Well, when does x cubed plus 4 equal to 0? Well, when x cubed is equal to minus 4. So when x is equal to the cube root of minus 4, which is equal to what? What's the cube root of minus 4? Negative 1 point. I'll just copy that, okay? There we go. Which means over here, at negative 1.587, is the other point it goes through. But that's it. Those are the only 2 points it goes through. Since we're dealing with a positive cubic, that tells me it's going to slip and slide through that and then come upwards through that. So we're dealing with something that looks like that, which means I'm going to have a point of inflection there, which just helps me to know this graph. It's going to slip and slide through there. I'm going to have a point of inflection, because it's turning down, I'm going to have another one there. This point of inflection here won't create a max. There's a point of inflection here, and there's going to be just a local min here. There's not going to be any other min because this slip and slides through there. How do I know that? Because if I've gone through the x-axis and I only have one other x-intercept, I have to come back up through it. I can't, I mean, I could do something like this, but because this is cubed there, all of it's happening there. So when you see a cube, you're almost always going to get a slip and slide situation. So I already know this is what it's going to look like. What else do I know about it? Well, that's a lot. So let's take the first derivative. And we're going to get 4x to the cube plus 4. And we're going to set that to 0. So you're going to get 4x to the cube is equal to negative 4. And we're going to get x cubed is equal to negative 1, which means when I take the cube root of that, plus 4 minus 4, x cubed is equal to negative 1. That's right. When I take the x cubed of that, I get negative 1, which means I'm going to have an inflection point here at negative 1. And when I plug that into the original equation, negative 1 to the power 4 is 1. Plus 4 times negative 1 is minus 4. So 1 minus 4 is minus 3. It's going to happen at minus 1 comma minus 3. So that's the only inflection point. Notice it didn't come up with 0 for the other one. But let's take the second derivative. Oh, that's not an inflection point, rather. I have to set it. That's where the slope is going to be 0, because I set it 0. So that means this little bottom part, is minus 1, minus 3. So I found the only min point as expected when I set the first derivative to 0. And the first derivative was 4x cubed plus 4 equals f prime. That's the first derivative. My bad. Now I'm going to take the second derivative. A derivative of 4 is nothing. So all I'm going to be left with is 12x squared. Okay. If I set that to 0, I will find the inflection point. And sure enough, when I bring 12 over, I get 0, x cubed, so the answer is 0, comma 0 when I put it back into this point. Which means, indeed, this is technically the only inflection point. Oh, and it wasn't there after all. So that means this whole thing came down through here, came up, and there's going to be some sort of turn that happens at 0, comma 0. So that's interesting. I didn't expect that. So regraphing it, I know it's coming down through here. I know it's hitting a min at -3. I know it's going through 0, 0, and then there's some sort of inflection point. Interesting. I would have thought it would more look like this. Slide. Hit a min. Go through here. And then I guess it does something like that. Which still surprises me that there's any wiggle. Because there's some sort of inflection point there. And 12x squared, just make sure it is indeed 0. When I plug the 0 in, I know what happens at 0, 0. Okay. Determine any points of inflection. I just did, 0, 0. But I also know that... Oh, by the way, if I wasn't sure if this was a min, I would plug in -1 into this equation. I get 12, which is positive, which tells me it's a concave up. So I do indeed know that that's a minimum using the second derivative rule. And it's the only minimum I found from my first derivative. Let's sketch it, see what's going on. Okay, yeah, it does do this weird wiggle thing here. See how it's hard to see it visibly. So let's see if I can make the y-axis just from -1 to 1. No, it's still not doing it. And let's see if I can make this scale -20 to 20. Maybe that'll help. Didn't help. Let's make this -11 to 11. Yeah, sort of. There we go. That helps a bit more. So you can see that point of inflection there. You can see the min that we got correctly. And thanks to that point of inflection, it actually corrected my drawing. So there's no point of inflection as it's going through here, which makes fine. That makes sense. There is a point of inflection here. So it helped me draw it a bit better. Doesn't look like a W now. Just to make sure, when does the first derivative equal to 0? That's the midpoint. When does the second derivative equal to 0? That's the inflection point. So there's only one inflection point. So we did it correctly, just the initial drawing was incorrect. We can also say when was f of x equal to 0, and it'll give us the, when is 0 equal to this formula, and it'll give us the x-intercepts. So you can see we get it all. The x-intercepts, the min point, and of course that is the inflection point. Let's take the other one and see if we can figure out what's going on. So that's a w cubed. So if we look at it, that's a w cubed. And we got a w squared up top. So we have a smaller power over a bigger power. And if you just kind of look at what's going on and cancel out, you have a 1 over w. Just to give you a rough idea of what's going on. So I think if I'm going to guess, and it's clear that there is a vertical asymptote at 0, that we're dealing probably with something pretty normal. Now we'll see what this -3 does. Let's look at infinity as well. When we're positive infinity, we get 4 times infinity squared. Essentially, that -3 doesn't matter. When we're positive infinity below, we get infinity cubed. Now, this 4 will not be that important. The horizontal asymptote will be at 0 because the power here is lower than the power here. So, ignoring this 4, we can see it's going to become closer and closer to 0. Because as these get huge, we're left with 1 over infinity. They cancel out, right? This cancels out entirely. Or 4 over infinity if you want, but it doesn't matter. So it gets closer to 0. As this gets negative infinity, this top part becomes positive. This bottom part becomes negative, but it's still coming 0. So that means the underside is coming up to 0. If you want to ever see if it crosses, you would make this equal to 0. You bring up the w cubed, it becomes 0. Oh, sorry, if you ever want to, if you want to see if it crosses 0, make it equal to 0. Bring that up, it becomes 0. You get 4w squared is equal to 3. W squared is equal to 3 over 4. So apparently it does cross when w is the positive square root of 3/4 and the negative square root of 3/4, which means that if I'm going to draw it, there's a horizontal and vertical asymptote on the x-axis, and this will come down and kind of cross the x-axis and then hug it. So we'll have to see if there's a local min there, because it might do this. And this other one does the same and then hugs. So that means at negative square root 3/4, whatever that plugs into, and positive square root of 3/4 x, comma 0, it will cross. Let's see if that's right. And that means there should be a local max and a local min. So let's go to the derivatives of this. Okay. There's the function. W cubed. So the bottom function is going to be w cubed, which means the derivative of the bottom function is going to be 3w squared. The top function is 4w squared minus 3, which means the derivative of the top function is 8w. You take the whole thing, you're going to square the bottom. What's the square root of w3? W to the 6. Learn your power rules. You're going to take the bottom term, and you're going to multiply it by the derivative of f of x. So you're going to get 8w to the 4. Then you're going to subtract the top derivative times the bottom derivative. A little harder, isn't it? 3 times w squared is going to be w4, and 3 times the 4w becomes 12w squared. 12w squared, or to the 4 rather, minus 9w squared. Now when I apply this negative to both of these, it becomes a negative here and a positive here. What's 8w to the 4 minus 12w to the 4? Minus 4w to the 4. I'm back to 4w to the 4. 4w to the 4 plus 9w squared. You can instantly see that 2 w's will come out here. This will just disappear. This will become to the 4, and this will become squared. So I'm left with, if I did it correctly, minus 4w squared plus 9 all over w to the 4. So that's the first derivative, and you can see how easy it is to make mistakes. If I set that to 0, I should discover maxes and mins. So you can see that the bottom doesn't matter too much. So it disappears. So I'm left with minus 4w squared plus 9 is equal to 0. When I take the 9 to the other side, it's equal to minus 9. When I divide both sides by minus 4, I'm left with plus 9 over 4, which means w is going to be equal to 0 when the square root, the positive square root of 9 over 4. What's the square root of 9 over 4? 3 over 2, which is something we discovered before. So there's going to be a which is equal to 1.5. So when x is 1.5, there's going to be a max or a min. And when x is equal to negative 1.5, because you have to take the negative as well when you take the square root, there's going to be a max or min. If we go back to our original equation and we punch in 1.5 squared times 4 minus 3, so 1.5 squared times 4 minus 3 divided by 1.5 to the cube, we get 1.77, which, and I hope that's right, which means here it becomes 1.5 comma 1.77 is the one intercept. And I believe for the other intercept, the only difference is it'll be negative. Yeah. Okay, so there are indeed maximums and mins. So that's our first derivative. And to find the inflection points, and this is going to say, I'm going to say this is our max and our min. And I'm going to say the left one, because we already determined it's going to look like this. I'm going to say this one here is the max. And this one here is the min. Now, we're going to use second derivative to make sure. We already know that the first derivative is this. And we go back and we do the whole thing over again using the quotient rule. It gets a little stickier the more you do it. Okay, the quotient rule says I'm going to square this at the bottom. I'm going to get w to the 8. I'm going to take the derivative of the bottom, which is 4w to the 3, and I'm going to multiply it with the derivative of the top. The derivative of the top is simply minus 8w. So when I multiply 4 times the minus 8, I get minus 32. When the w's multiply, I get w to the 4. So that's so far so good. It's all going to be over this, by the way. Now I have to subtract the top function. And it's all treated, that minus is the bracket, times the derivative of the denominator function. The denominator function is quite simply this. Now again, you have to treat like this is in brackets. So we multiply this way. I get minus 16 w to the, oh, I got the wrong one, it's w to the 4. Oh no, the derivative is w to 3. So I get minus 16, which makes me think, yeah, this first one here should be w to the 5 here. There you go. Made a small error. So this second one, 4 times the minus 4 minus 16, w3 times w to the 2 is w5. So I get minus 16 w to the 5. And then the 4w squared times the 9 becomes plus 4 times 9, 1836 w cubed. Now, this subtraction applies to both those things. So this becomes positive, and this becomes negative. So when I look at minus 32w to 5 minus, plus now, 16w to the 5, it becomes minus 16 to the w5. So I can just take this w5 and put it in front of that minus like that. And the second one becomes a positive 36. Now I didn't have to simplify. I could have actually just left it and plugged in to make it equal to 0. Actually, I do have to simplify. So I'm left with that. Now, if I simplify the bottom, these W3s disappear. These W5s disappear. No, I can only simplify, I can only take W3 out of it. So this becomes a 5. This 5 becomes a 3. And this W disappears. So this is the derivative. Minus 16w3 plus 36 over w to the 5. Pretty complicated. Now, I have to set it to 0 to find inflection points. Obviously, the w to the 5 doesn't matter. I get minus 16 w to the 3 is equal to minus 36. Might be minus 38, but anyway. When I divide it by minus 16, I get positive 36 over 16. When I divide them both by 2, I get 18 over 8, which is 9 over 4, which is as far as I can go. Which means the inflection point will occur at the cube root of 9 over 4. Let's take 9 over 4 and take the cube root. Now you can see that I probably made a mistake here because it's a pretty odd number. So it's saying that when x is 1.03, and I should have come up with a negative one as well because there should be 2 inflection points, which I didn't. So I probably made an error on the second derivative, which just goes to show you how easy it is to make an error. So let's just graph it and see what we came up with. 4w squared minus 3. Let's do it 4x squared minus 3. All over w to the cube. X to the cube, rather. So at least we guessed correctly what would happen. Let's find out when this is equal to 0. Well, we can just do it. There's the points that we felt were the x-intercepts. There are indeed the max-mins that we said were 1.5 and 1.4. And there should be an inflection point because this is going up and this was going up. There should be an inflection point out here and out here. So we already discovered one of them. So we're going to take the first derivative and set it equal to 0. That'll give us the max-mins. And we're going to take the second derivative and set it to 0, and that will give us the inflection points. So I did indeed do the second derivative incorrectly because the inflection points occur at 2.14 and negative 2.14. Makes sense that there was mirrors, so I'd have to go back and take the derivatives twice. So 4x squared minus 3 over x cubed. This is where Symbol Lab is good. And I think I got the right first derivative. Here's the first derivative. Yep. At least I got the first derivative correct. And where I screwed up was the second derivative. So we're going to take minus 4x squared plus 9. And we're going to take the derivative of x to the 4 at the bottom instead of x to the 3. And we're going to hit go. And here's the second derivative. Yeah, I got it well wrong, I guess. Yeah, it should have been squared up top, not cubed. This is the second derivative. Now that still translates to minus 8. Oh, a big minus in front. So it's minus 8 cubed, 8 squared, minus 36. They should have really applied this minus twice, because it should be that. It's the same thing, over x to the 5. So I screwed up somewhere where I got x cubed here instead of x squared, which should it have happened at 3? Yeah, x to the 3 brings this down to 2. Stupid. And then I would have discovered that x squared or 8x squared is equal to 36 minus, yeah, that would become a positive and that would become a negative. 8x squared is equal to 36. Then x squared is equal to, I was close. I had 36 over 8 as x cubed, right? Instead of 36 over 8, which is 18 over 4, which is 9 over 2. So I had a cube root of that. It should have been the square root of that. So the only thing I screwed up, I think, is the square. And that's just a really basic cancellation mistake. Almost got it. But the good news is that graph is very much as we had thought it would be. So f of 1.5. So that's that one. And that's that one. And I think it was negative 2.1. So that's the point of inflection, roughly. I guess I can do the square root of 9 over 2, comma, f of the square root, 9 over 2. So that's that one. And then I can make another one where I make them both minus. So there's the inflection points where the graph starts to turn and flatten out. Since they're pretty much mirror image, it makes sense that there'd be 2 inflection points. And when you make a calculation error, you should immediately say, oh, I did something wrong. Good. Let's keep going. Sketch the graph of a function with the following properties. No, come on. Find constants a and b. Okay, this is doable. I'll leave 9 to your teacher. I really don't want to do hypothetical graphing, trying to deduce what the graph is. I mean, I can with time, but to me it's a waste of time. So, they want to know when we're going to have an extreme point with this, which means the derivative of this is going to be at 0. And when will inflection be this, which means the second derivative equaling 0 will produce a 1x. Sketch the graph. So we're dealing with a cubic, and the question is just when will it be equal to 0? It looks like I have to stop soon. Do that. So what's the derivative of that? It's going to be 3ax squared plus 2bx is equal to the first derivative. And the question is, we're told that when x is 2, we're going to get a 0, because that's when an extreme would be. So when 2 squared times 3, I get 12a. So essentially going to get a formula. 12a and 2 times 2 is 4b is going to be equal to 0. So that's formula number 1. Now we're going to take the second derivative of that, and we get 6ax plus 2b, and they've told us this is going to be 0 when x is 1, because when the second derivative, which this is equal to 0, you will get the inflection point, and they've told us when it's 1, which means I can rewrite this equation when x is 1 as 6a plus 2b is equal to 0. You now have two formulas and two missing variables. So if I rephrase this as b, I get 4b is equal to negative 12a. When I divide both sides by 4, I get b is negative 3a. If I go down here and rewrite b as 2 times negative 3a, I now get negative 6a. Well, that's not going to help me. So it's saying a is 0. No, that's not going to do it. 6a plus 2b is equal to 0. 12. Yeah, the problem is they're both the same formulas. (3ax squared plus 2bx is going to be equal to 0 when x is 2. So I'm going to get 12a plus 4b. Is that what I got? Is equal to 0. That's what I got for this first one. Good. Then the second derivative is going to be 6ax plus 2b is equal to 0. And when x is 1, I get 6a plus 2b is equal to 0. The problem is this formula is the same as that formula. So it's not going to help. However, I am going to get another formula from the formula itself. Since I know that this is going to be equal to that when 2 is 11. So I'm going to get another one. So when y is 11, I'm going to get 2. I'm going to get a. And what is x, 2 to x? 8a. Plus, and when y is 11 and b is 2, 2 squared is 4b plus c. And I'm also going to get another point that when y is 5, x is 1, so I'm going to get a plus b plus c. And I finally have the other formula, which is 6a plus 2b is equal to 0. I now have 3 legitimate formulas. How I got up with these other two is because I had a y and x value that will fit on the graph, right? It has to fit on the graph. So I'm going to get rid of this. And now that I have 2 formulas, we're going to look at the second formula, in which I just determine that b is equal to minus 3a. If I replace it up here, I get 5 is equal to a plus minus 3a, which is minus 3a plus c. So I get that c, or that a, so minus 2a now, plus c, so I get minus 2a is equal to 5 minus c. And since I know b, well, actually I should do it in terms of c. Yeah, let's do it in terms of c. So I get 5 is equal to a minus 3a plus c. So that means c, if this is minus 2a, is equal to 5 plus 2a. Now I have terms for b and for c in terms of a, which means I can go to the first equation and do 8a and replace b with plus 4 times minus 3a, which is minus 12a. And I can replace c with what I know is c down below in the other equation. So I get this. 8a plus 2a minus 12a is minus 2a. Plus 5 is equal to 11. Which means minus 2a is equal to 6, which means a is equal to minus 3. If a is equal to minus 3, c is equal to 5 minus 6, which is minus 1. And therefore b is equal to negative 3 times negative 3, which is 9. So I needed 3 separate equations, and I got them. I just couldn't use the derivative and second derivative twice, which means the formula for this equation is y is equal to negative 3x cubed plus 9x minus 1, which means it's a reversed cubic. I know it's going to go through the x or y-axis at 0, minus 1. Can I have a, no, can't find the x-axis. I know it's going to have a point of inflection at 1,5, and at 2,11 it's going to hit either a max, but I know this is a negative, so it's coming down. It's crossing through. Coming down, crossing through. I can do that. Oh yeah, it's going to do this. Come here, and then go down. So this inflection point will happen here, 1,5, and this will be a maximum at 2,11. Now I could take the first derivative, second derivative, and figure it all out. I could also take the quadratic function and figure out where the two x-intercepts are. I know it goes through because it has a y-intercept of c, and I've determined that the c is minus 1. Let's see if I got the right answer, or if I did the equation all screwy. And this is question what? What question is that? Question 10. And I might have to stop. No, I got it. There we go. So there's the two x-intercepts down there. There's the y-intercept. There's the inflection point, and there's the max. And then there's another x-intercept here. If I put it here, get rid of everything. And that's what I get. Oh, I got one of them wrong. Plus 9x minus 1. Oh, I got this as a cube. No, it was a cube though. Oh, I know what I just wrote down the square wrong. There we go. So I can see there's x-intercepts there. So if I could figure out any factors of the cubic, so there's no way I was going to come up with the x-intercepts. But there indeed is that. And somewhere in there, 1 is 5. And somewhere in there is 0, minus 1, which is down there. So there you go. The only thing you couldn't come up with is the x-intercepts, because there's no way to factor that cubic. Oh, but there is this 5, 11, no, a 2, 11, which is the max. So there you go. We got it right. Now I'm going to have to take a break, which is unfortunate. Show that this has 2 points of inflection. Show that the x-coordinate is one of those points lies midway between the x-intercepts. I don't know if I can do that quickly, but I will try. Oh, I missed C, but let's just see. Let's go do 12 first. Okay. So that means if it has 2 points of inflection, the second derivative. So let's take the first derivative. Cubed plus 3bx squared. Let's take the second derivative. Six bx, which I think is that. It needs to find if there's 2 points of inflection. So if I factor out 6x from both, I get ax plus b, which means there's going to be a point of inflection when x is 0. So at 0, 0, there will be a point of inflection. And the other one when x is minus b over a, add f of minus b over a, whatever f of minus b over a is, will be another point of inflection. So there are indeed 2 points of inflection. The x-intercepts depend on the factors. So I can factor out both. I can factor out x squared. Right? And I'm left with 4x plus 3b, which means the one x-intercept will be 0, 0. And the other x-intercept will be at minus 3b over x. No, over 4. There we go. Now, since one of the x-intercepts is minus b over a, oh, we forgot the a. So if I take that out, it's 4a, so over 4a here. Since one of the points of inflection is minus b over a, and the other one is minus 3 times b over 4a, don't know if I can prove it's halfway between the x-intercepts. So what's halfway between these x, 0, 0, and minus 3 over 4ba? What's the halfway point? Oh, I took the wrong x-intercepts. The x-intercepts I have to take from here. So if I get x to the 3 out of both of them, I'm left with ax plus b, which means the x-intercepts are 0, 0, and minus b over a. Which is not what I got for, oh, here we go. This should have been up here. 2ax right there, which means it's minus over 2a here. Ah, which is indeed halfway between minus b over a. So if this is the x value of one of the x-intercepts, and this is clearly half of that, that means the point of inflection is indeed halfway through the x-intercept. So you can do it. I just did it incorrectly. Find the value of the b constant such that this function has a point of inflection at x is equal to 3. So that means the second derivative will equal to 0 when x is 3. That's a lot of work, so I'm going to save those last 3 for the next one.